Now, refrigeration. Okay, so the first part of refrigeration, we will be referring to reverse Carnot cycle, the reverse Carnot cycle. So for heat engine Carnot cycle, we have heat flow from warm environment, that means from high temperature region, actually from high temperature region to lower temperature region. But as for reverse Carnot cycle for refrigeration, we have the opposite direction. So the temperature the heat is flowing from lower temperature region to higher temperature region. So the lower temperature region here, we call it as the refrigerated space. The refrigerated space. So anything that you put into this refrigerated space, let's say chicken or milk or water, that is with relatively amount of heat. When you place it into the refrigerator space, the system in the refrigerator, the system here is the refrigerant. The refrigerant, that means the cooling agent. It will tend to absorb or take away the heat from the stuff that you put into the refrigerator space. So the heat goes into another device which is working at higher temperature, at a higher temperature level. So before the heat can move to the higher temperature level, that means a higher temperature region, you need a push. The push is provided by the work input. And the device that we use here is usually the compressor. The vapor compressor. And then the refrigerator space usually we refers to the evaporator. The evaporator. And the warm environment, that is the atmosphere. Before going into the warm environment, so actually the refrigerant will go into a condenser, where it is being cooled and recycled. So the heat will be rejected to the environment. It's just like your household refrigerator and your air conditioning. Both of these devices do the same thing. They reject heat to the environment. To the environment. So the device that we use for work input is a compressor. For heat engines is a turbine, where here you have work output. And for his engine cycle, usually the arrow is pointing downwards. This is pointing upwards. So with the help of the compressor, circulating the refrigerant or bringing the pressure up to a certain amount of pressure with relevant high temperatures. So here is your compressor. This is the condenser. Usually condenser is a condensing tubes and evaporating tubes. And then, in actual case, this is an expansion valve. So this is your refrigeration cycle. So on the TS diagram, the same thing. It works based on the same thing, a square. And then it means that it is two isothermal process and two isentropic process. The only thing is, when you look at the arrows, they are pointing towards the anti-clockwise direction. It's in the anti-clockwise direction from point 1, 2, 3 to 4. So, and then you have two pressure limits. One is the evaporator pressure based on this, and then the condenser pressure based on this. So that is the reverse Carnot cycle. Now, for TS diagram, the area under the process path from 2 to 3. This section here, or this process here, should be the condenser. The condenser. So what happens here? You have heat rejection. The heat rejection to the environment. There's a decrease in entropy, so it's heat rejection to the environment. So to find this heat rejection, the same thing here applies. Find the area under the process path from 2 to 3. That is the height multiplied by the base. The height is TH and the base can be S2 minus S3 or S1 minus S4. That will give you the heat rejection. Okay? So, now usually we found that the reverse Carnot cycle is not a suitable model. Even though the heat engine Carnot cycle is also not a suitable model as compared to real practice. Okay, as for real practices. Okay, now the first thing is process 1 to 2 is a compressor. The device that we use for the process state point 1 to 2 is a compressor, and it cannot be dealing with two-phase substances. That means liquid and vapor. So a compressor can't handle two-phase. It's just like a pump. Also, it can't handle two-phase. Okay, that is the saturated liquid and dry vapor. Okay, and here you have the vapor. Okay, and the vapor and the liquid as well. So two-phase substance which involve the compressions of liquid vapor mixture cannot. So, and then the second point is why it is impractical. Why the reverse Carnot cycle is impractical as for a refrigeration cycle is process 4 to 1. 4 to 1 here is where you have your evaporator. The device that we use here is the evaporator. Okay, so expansion of high moisture content in a turbine. If let's say for example, if this is a Carnot cycle, 3 to 4 would be a turbine. It would be a turbine, not an expansion valve. It would be a turbine from 3 to 4 for Carnot cycle, reverse Carnot cycle. So process 4 to 1, expansion of high moisture content. This whole thing here is of high moisture content from 4 to 1. Okay, in the turbine, and that means make it unsuitable. Okay, you know when turbines deals with high moisture content, what happens is erosion will take place. The wear of the turbine blades will take place faster, and it requires, if you use a turbine, it requires a large flow area, and the next thing is unaffordable, okay, if for domestic purposes. If let's say for example, if you were to buy a refrigerator which costs you few $1,000,000, I don't think so. Nobody is affordable to buy such refrigerator, okay, with a turbine. Okay, so based on energy balance, I've already said earlier, energy balance, then you have to look at the arrow that we have here. The input, one of the input is this, and then the second one is this. This is the work input, that is energy input, and this is another energy input, that is heat absorption. This is heat absorption by the system from the surroundings. From the surroundings means can be chicken, can be cakes, can be vegetable, your fruits and all those things. Okay, so once you place into the refrigerator, okay, the refrigerants in the evaporator tube will start carrying the heat away continuously in a cycle. So that is why we call this as heat absorption, and this is heat rejection. So this energy here plus this energy here must be equals to this energy here. In plus in equals to out. Okay, the energy balance. So that means you have your work in plus your heat absorption, or RE. Sometimes this heat absorption here we call it as RE, means the refrigerating effect. The refrigerating effect. That means the cooling effect. Okay, so this plus this equals to this. So the work in would be equals to, therefore if you manipulate this, you will have QH minus RE. QH, heat rejection, minus refrigerating effect, you get how much of work input. Or you can put W in plus RE equals to QH. Okay, in plus in equals to out. Now continue from the previous slide. Okay, this area here I've already told you that is the area for heat rejection, and this is the formula based on the area of this rectangle under the process path from 2 to 3, that is heat rejection. Then when you look at the next page here, this is where you have your heat absorption or the refrigerating effect. So that is based on temperature TL. So as you can see, it's pointing, the arrow is from 4 to 1. That shows there's an increase in entropy. So that means some heat energy has gone into the system. That means the refrigerant. So that would be the refrigerating effect or heat absorption or cooling effect, okay, by the refrigerant. So the area bounded by this will be equals to your heat absorption or refrigerating effect. Okay, so that is the refrigerating effect, RE equals to the height multiplied by the base. So here, the refrigerating effect or heat absorption. Now, the next thing that we have to discuss is about the COP. Now, COP is known as the coefficient of performance. Now, for refrigeration, we don't call it as efficiency. We don't call it as thermal efficiency or efficiency. We call it as COP, that is the coefficient of performance. Now, how to define the COP or the coefficient of performance? So it's just the same as what we have done for heat engine cycles. It's defined as desired output divided by its required input. So what is the desired output of a refrigerator? Is the cooling effect or the refrigerating effect. That is the desired output. And what is the required input? That is the work input from the compressor. That is your power supply. So that is your required input. So therefore, for refrigerator, since the desired output is to give a cooling effect, so it would be the RE, the refrigerating effect, divided by the work in. Now, on the same cycle, also you can look into something which we call heat pump. That is the condenser part, heat pump. That means you are ejecting heat or discharging heat or supplying heat energy to an environment, especially colder countries. Okay, you require a heat pump. So if you revert or convert, that means from a refrigerator, actually you will get a heat pump. So heat pump is where your condenser is. So if it is COP for heat pump, then your desired output should be the heat rejected, not the refrigerating effect. The desired output of a heat pump is to supply the environment with heat. So that is the desired output, so that is the heat rejected, not RE. And the required input is still the same, work in. So what you need to do is just substitute your RE, your work in, so you'll get your COP for HP and the COP for refrigerator. Okay, so also based on this is called the energy balance. Yeah. Now dividing throughout the whole equation here with work in, you see here. So QR over work in is actually a COP for HP. Work in over work in, you get 1. RE over work in is actually a COP for refrigerator. So if let's say for example you take COP for HP minus COPR, you actually get a 1. Okay, that is based on your reverse Carnot cycle. Okay, so basically this is your reverse Carnot cycle. This is the schematic diagram of your reverse Carnot cycle. Compressor, condenser, turbine, or an engine or expander, and an evaporator. Here we don't call it a turbine. Okay, So as you can see, point 4 is inlet to the evaporator, the cold region. Outlet, point 1, compressor, inlet, the suction line and the discharge line, then to the condenser, okay, inlet, outlet, and then to the expander, inlet and outlet. So usually heat absorption is from here, heat rejected is from here, work in is from here, and here usually you have a slight little work output. Okay, but then usually we don't employ or we don't use this device unless you are referring to a refrigerating truck. Okay, otherwise for domestic usage, usually this is replaced by a capillary tube or an expansion valve, where the process becomes irreversible here usually. So this is your TS diagram. That is your evaporator pressure and condenser pressure. Now, reverse Carnot cycle will be replaced by what we call a simple vapor compression cycle. Okay, reverse Carnot cycle replaced by simple vapor compression cycle. So because reverse Carnot cycle is not, even though it is an ideal cycle, but it is impractical to work as a refrigerator. So therefore, it is being modified and it is called a simple vapor compression cycle. So the turbine is replaced by a throttle valve or a capillary tube, or the engine is replaced by a throttle valve or capillary tube, or what we call an expansion valve. Lower in cost when you replace it with a capillary tube, which is very cheap compared to a turbine or an engine. Lower in cost and affordable. Don't need large floor area. Okay, so it is actually negligible area. Now, which is also cheaper and economical than 5.5, but the process, now this is the disadvantage, but the process has become irreversible, and it is shown on the line later on 3 to 4. Later on, this is still reverse Carnot cycle. Later on, 3 to 4 will become dash line and not vertical. Okay, then also lower cooling effect. That means if, let's say for example, you replace it with a capillary tube or an expansion valve, the refrigerating effect is being reduced. The cooling effect will be reduced. And of course, during this irreversibility process of the throttle valve or the capillary tube, you have constant enthalpy. And that is when constant enthalpy process comes in. Okay, so I think we will stop here today for this section, this slide. Okay, and we will continue with the next slide on the next podcast, sorry, because I will try to cut short the time of each podcast. Okay, so that it won't be so long. So here are the different type of vapor compression cycle for refrigerators, which will be explained in the next podcast. And these are the principal parts. Okay, I've give you some explanation or the applications and the name of the devices. Okay, and this is your tutorial. Thank you very much. We'll continue next slide. Thank you.